Okay, there we go. And it's the, oh, it's May. Happy May Day.
Yeah, it's International Workers' Day.
It is. Workers of the world unite. So, anyway, this stuff will be on the quiz at the end of the unit. Capacitors are devices for storage of charge. And the most common kind is what's called a parallel plate capacitor. You have two plates that are, you guessed it, parallel to one another, and you know that from geometry. And there's some kind of gap in between them that has some sort of insulating material. Remember that air is an insulator. So you can have two parallel plates that just have air between them. You can also have other sorts of insulating material between them, and basically you build up charge on one plate sufficient to, you have one of two options. You can have a situation where you build up so much charge that it then jumps the gap. And if you think about our discussion of lightning the other day while we were using the Van de Graaff generator, when you have two areas of charge, two fields, and finally the charge builds up to a point where they connect, that's that static spark we see as lightning, you can have a parallel plate capacitor where it charges up to a certain point, then discharges, charges up to a certain point, then discharges. So it provides a sort of pause in a circuit. You can also have a parallel plate capacitor where in some way you change the position of the plates, and that's what discharges it. Capacitors, so capacitance is the ability to store energy. Capacitors are why even a circuit that is disconnected from power can give you a little bit of a shock if it's got a sufficiently sized capacitor in it, because there can be charge left in the circuit even after it's been disconnected. So I don't know if any of you have had the experience of taking apart electrical things. You should. Go to Goodwill and buy like cheap clock radios and tear them apart and figure out how they work. Seriously. But you can have capacitors in a circuit. Now, slowly that charge will leak out. It doesn't hold forever. So something that's been sitting on the shelf at Goodwill for 6 months isn't going to give you a big shock. But if you've had it plugged in and you take it apart and a few minutes later you start to tear into the circuit board, it's quite possible to get a shock based on little small capacitors that are typically in those kind of electronic devices. There are systems with much larger capacitors, and you might guess that the larger the capacitor, the longer it stores a charge. Depending on which kits we get, and we're going to have a discussion of that, one thing that you'll see is a thing that looks like a little cylinder with a couple of legs, and that's your capacitor. Huh? And, you know, that doesn't look like this. It doesn't look like two little plates with, you know, lines coming out of each side of them. Because what they've done is taken those two plates, and I'll make the wires a different color for clarity's sake, and they've rolled them up like a jelly roll, and I can't do it justice. But what you end up with is this thing that looks like a little tiny cylinder, and it's actually a capacitor that's rolled up on itself. Pardon?
That's pretty smart.
It is, and we'll look at some examples. I'll get out some capacitors that you can look at. Okay, so this brings us to current. And current is what you get when you have a net movement of charge. When charges are moving through some medium, like a wire or air or water or anything else, you know, an entire circuit. And current is the rate at which charge moves through an area of wire, some given area. So current is given, it's in equations, it's shown as the variable I, capital I, and it is charge per unit, change in charge per unit time. So how much charge, it's a rate. Current is a rate. And we'll get into all the analogy waters for current. Okay. So amps are what we measure current in. 1 amp is a coulomb per second, capital C over S. And this brings us to sample problem 19A. Page 695. Forgot to hit record. So current in a light bulb is 0.835 amps. How long? That's a clock for those of you who can't figure out my cryptic little drawings. For 1.67 coulombs of charge to pass through the wire in the bulb. I is equal to the change in charge over the change in time, solving for delta T. So delta T equals the amount of charge passing that point divided by the amount of current. And what we get, delta T equals 0.835 coulombs divided by 1.67 whoops. Sorry, 0.835 amps divided by 1.67 coulombs. Okay, so we get a raw answer at 0.5 seconds, but let's check this dimensionally. And 1 amp equals 1 coulomb per second. So we have a coulomb per second divided by a coulomb over 1. Oh yeah, we're getting the inverse, aren't we? What did I do? I flipped my thing. Wait a second. Okay, I didn't flip my algebra, I flipped my plugging it in because, you know, any drunken chimpanzee can do 3-part algebra, but one physics teacher who hasn't had her second cup of coffee can't plug in her variables correctly. Sorry about that, folks. Let's just get rid of that, shall we? So, current is in amps. And I went ahead and, you know, the thing that current is I. The thing that I continually tell you people to do, list your variables, which I didn't do, and then I can't plug it in if I don't list my variables. So, plugging in. Good morning. How are you? Delta T equals, Q is charge, which we remember from Coulomb's law problems briefly. 1.67 coulombs divided by 0.835 amps. And so we get as a raw answer 1.67 divided by 0.835. We get delta T equals 2 seconds, which we would have known, and it would be 0.200. And of course, 1 coulomb divided by a coulomb per second, invert and multiply, we get seconds. It works out dimensionally. Dimensional analysis is so handy. Okay, so 3-part algebra, if you list your variables, you're less likely to make really dumb mistakes. Pretty straightforward, pretty simple, and these are literally just 3-part algebra. So I'm assigning numbers 1 and number 4. Okay, so current flows from high to low. It's just like gravitational potential energy in that, and we will use some multimeters a little bit later to measure potential difference across a circuit. So you can create potential difference with anything, and that's just like pushing the rock up the hill. That's creating the potential difference. You can do that mechanically, you can do that chemically. Then when you release it, it's going to flow downhill. And we have alternating and direct, which we'll talk about here. So in direct current, you actually have charge carriers that are moving. They are changing location. They are flowing through the circuit. And batteries provide direct current. So in a battery, you have 2 terminals. Who here has stuck a 9-volt battery on their tongue? Do I have to assign homework? Really? Okay. And you shouldn't, I should say, I'm joking, you shouldn't ever put a 9-volt battery on your tongue, kids. That's how I test them at home. You know, and if you get a little zzz, then it's good. Wait, what are you doing when you stick a 9-volt battery on your tongue? You're making a circuit. Your tongue is the circuit. You're connecting the terminals, and you're getting 9 volts of current across your tongue. I'm sorry, 9 volts of electricity across your tongue. So, it's actually electrons flowing across your tongue from one terminal to the other. Because basically within that battery, the easiest way to imagine it, and this is again not precisely correct, but it's a good way to imagine it, is a division here. And we stack up electrons on one side and we empty them out of the other. When you connect those 2 terminals, electrons want to flow to the lowest energy area, to the area that doesn't have electrons. So alternating current is a little bit different. The electrons don't actually move, they vibrate back and forth. They alternate direction, the charge carriers. And what we look at is the frequency of vibration, and frequency is measured in hertz. In the US, the standard is 60 cycles per second. Oh, actually, wait, it's not. Maybe it's not voltage. Maybe it's frequency that is the difference coming out of the socket. We'll have to look it up. Batteries provide DC, but you can run the current from a battery through what's called an inverter and cause it to create AC. And has anybody here ever spent time in an RV of any sort? or a van with camping capacities, there's typically an inverter somewhere in there, because that way you can plug your standard coffee maker into an outlet in the trailer if you're on the road. Because you're typically drawing your current from an extra battery. You have a sort of a backup battery that provides power. And to plug a standard wall outlet in, you have to either you either have to have what are called DC appliances. You can make a generator that provides AC or DC, and if you have a generator at home for like emergency power outage kind of use, typically those have an inverter built into them so that you can plug them directly into your home's power supply. If not, you have to have an inverter or you'll blow all your stuff up. Okay, so you know what power is. It's how fast work gets done. And electrical power is how we change the rate of electrical potential energy over time. So change in potential energy, electrical potential over time is power. And voltage, the change in voltage was, that's wrong, delta PE over Q. So electrical power is equal to current times change in potential energy, change in electrical potential. Yeah, we're not going to use it. So yes, I'd like you all to say together, Get it? Ha 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 ha. No, you're resistant. Ha 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 ha. You don't even know why that's funny yet. But it is. So, most materials have some level of resistance to the flow of charge, and it is a characteristic of the material. Just like friction coefficients were characteristics of the surfaces, resistance is a characteristic of the material. Materials that have very low resistance are what we call good conductors, and materials that have very high resistance are good insulators. So, there is some constant number to the amount of voltage that can flow through a material. The change in electrical potential over the current is equal to some constant. And as long as that's true, we say the material conforms to Ohm's laws. They are ohmic. Ohmic, which is a nice little word. For materials that don't, so have you heard of semiconductors? You're sitting on one or sitting in front of one. Computer chips are made of a semiconducting material called silicone, largely, and semiconductors change their behavior based on conditions of temperature or current, and those are called non-ohmic. So they are not a straight linear relationship with a constant resistance. Okay, so in a conversation up here, somebody was asking about current and voltage, and I'll use this again, but what I call the water pipe analogy. So if you have water in a pipe, and you think about current in a wire as water in a pipe, the current, the charge itself is the individual water drops. The number of those water drops which can pass a given point in the pipe, we can make a little counter of some sort in the pipe. The number of those drops that pass that point per second, that's the current. The force with which they come through is essentially the voltage. We haven't really talked about voltage yet. We're going to very soon. But the resistance is basically how much sort of friction, how much internal friction there is to that water moving through the pipe. The smaller the pipe, the higher the friction. More of the water is contacting the sides of the pipe. The bigger the pipe, the lower that friction, because less of the water is contacting the sides of the pipe. It's not a perfect analogy, but it's a pretty good one for understanding resistance. The farther you have to go in that pipe, typically the higher the resistance. So if you have current traveling through a meter of wire versus a couple centimeters of wire, you're going to have higher resistance over a longer distance. the smaller the wire, the higher the resistance tends to be. So just like with a water pipe, smaller diameter of pipe would mean higher resistance. Smaller cross-sectional area tends to mean higher resistance. Now this is an interesting one. Resistance tends to increase with temperature. So the hotter you get an ohmic material, typically the higher the resistance. And there are ways to work around this. And most circuits that you use every day have means to overcome this. But colder temperatures actually promote the flow of electrons. Years ago I had a Ford Ranger that had this peculiar quirk. You could get it in the morning, start it up, drive it anywhere. No problem. You could turn it off, no problem. You couldn't turn it back on again for an hour. So if you forgot and turned it off, you were going to sit someplace and have a cup of coffee, read a book, be late for wherever you were going. There was actually a circuit component in the truck that was heating up, and it was a relay. And you know, the factors that are used in that kind of circuitry to overcome increased resistance with heat had worn out. And so when the relay got hot, it didn't work anymore. It blocked current. It acted as sort of a fuse breaker, and current wouldn't pass, so the truck wouldn't start. $10 relay fixed the problem. It took me longer than I'd care to admit to do that. But that's because resistance tends to increase with heat in most materials. Okay. So here's where we're going to start to get into the use of resistors to create circuits. So resistance can be used to control the amount of current flowing through a conductor. This is what we typically do with resistors and circuits. We control how much current we get based on the amount of voltage we have in our power source, and we change the resistance to get the amount of current that we want for some device. So we put a different resistor in, we get a circuit that provides the current we want. If you would look at page 702, these are the 19B problems. Okay, every appliance you've ever touched or plugged in has some amount of internal resistance. And so they're saying that we have this steam iron, the resistance inside the appliance, inside the circuits is 19 ohms. By the way, the ohm is the unit for resistance. So what's the current in the iron when it's hooked up to 120 volts, which is your household current? Okay, so the voltage, delta V divided by the current, gives us resistance. If we're solving for current, we'll see if Moser can do three-part algebra correctly. Delta V over R gives us I. The voltage is 120 volts. The resistance is 19.0 ohms. That gives us I, which is... Okay, so we get 6.3157. We only have 2 sig figs, so 6.3 amps would be the current through the iron. Assigned are numbers 1, 3, and 5 on page 702, and I'll give you some time to do that. So, numbers 1, 3, and 5. I'm sorry, 703. These are the 19B problems.